Okay, so now that we've explored correlation a little bit with the applet on our textbook website, let's take a look at some examples of how we would apply this concept of correlation or association. So in the first example, we have a weight and a height situation. Tim wants to know if there's a relationship between height and weight. Kelly wants to know if she can predict a student's weight from his or her height. Information about height is easier to obtain than information about weight. So what we want to think about is what this scatter plot would look like reasonably logically. Would one of these variables be more likely to predict the other? And generally what happens in that case then, we want our x variable down here. This is going to be our explanatory variable. And then the y variable is what we call our response variable. So what we're looking for in a situation like this is one variable generally explained by the other variable. And in the case of height and weight, I think it's reasonable to say, and especially with some of the hints they're dropping here, height is easier to obtain. So we would it would make sense for height to be our explanatory variable. And then weight would be our response variable. When you think about this situation, generally, as somebody gets taller, they're going to be heavier in general. So that in this case, there would be a real clear explanatory and response variable. If we had a situation like, let's say, SAT math, SAT verbal. In that case, I don't know that either one really explains the other one. You probably would see a very strong association or correlation between the two. Generally, somebody who has a high math score probably has a higher verbal score in general. I realize that some people might be better at one or really exceptional at one and then really struggle at the other. But I think in general, if you see people that get higher scores in general have higher scores of both rather than lower of one and higher of both. I don't think you'd see a negative correlation between those two. But neither one is really a clear explanatory variable in that situation. Okay, the next one, I left the scatter plot on here just for convenience sake. But one of the things we want to be able to do is make a scatter plot, and I'd like you to lean on your calculator for that. So if you want to make the scatter plot on your calculator, remember the first thing you have to do is communicate to your calculator that you have some data that you would want to enter there. So just like we did when we only had one variable data, we go to Stat, and we're going to go to Edit first and foremost. So I go to Stat and Edit, and this is where I will take my time and make sure I copy those two lists incorrectly. You don't want to miss a decimal place somewhere, and it'll mess up your whole scatter plot. So I enter the two lists in my list editor on my calculator, and now I'm going to plot them. So instead of like in algebra and pre-calculus, you use the y equals button a lot. We are using the stat plot just like we did in the first couple of chapters for histograms and box plots. So I'm going to press second and the y equals key, and that gets me to my stat plot menu. So you can see that my plot 1 is actually turned on right now. I have it on, and I have scatter plot selected. That's what I want. So if you remember from the last chapter when we wanted to get the window sort of automatically, intuitively, we press zoom and then the number 9. Zoom 9 will automatically zoom in on our scatter plot, and you can see we have a very similar scatter plot here on our calculator that we have on the worksheet. So while we're here, I'll go ahead and flash forward to the next section. I won't go too deep into this, but if I wanted the equation of the least squares regression line, which is in the next section, and which we also saw in our introduction here, there we're going to hit the stat button again. We hit stat, but this time we're going to go to calculate. And what we like in statistics usually is this number 8 button here, the linear regression a plus bx. So a is going to be the y-intercept, b is going to be the slope. That's kind of how your textbook authors and also the College Board worksheet puts out those variables. So I hit 8, linear regression. If you don't get a setup that looks like this, I'll show you what to do in a second. But what you are going to want to do is look up this variable y1 so that we can graph the least squares regression line equation. Okay, so here where it says store regression equation to, and even if you don't have this menu, remember these steps. You're going to hit the variables key. I hit variables. I'm going to go over to the y variables key, and I'm going to select function, the first one, and there's my y1. Okay, you don't want to just type in y1. All right, so remember those steps. If you don't have this menu, that's fine. I'll show you what your stream will look like. Okay. And also, if you don't get r and r squared, I'll address that as well as a couple of steps that you want to follow here so that you do have those. So if you don't have the pop-up menu like I had, you would just type in linear regression. To get L1, remember you're going to hit second and the number 1. Right, I hit the second button here and the number 1, and I'll get L1, comma, second and the number 2 for L2, comma, and then Y1. And then when you press enter, you'll get that. Whoops. Bring back that last command. There it is. Okay, so if you're not getting the r and the r squared, what I want you to do is go to your catalog. So your catalog key is down here above the 0, so you're going to hit second and the 0 button. And what you can do here to shortcut this, you want to go all the way down to the D's. So if you hit your X inverse key, it'll take you down into the D's. And you want to find a command that reads diagnostic on. Okay, if we execute this command, it's going to appear as though nothing has happened. But behind the scenes, inside your calculator's brain, is going to know. So we're going to press enter again. So once you see that diagnostic on has been executed, now when you hit your linear regression, you should get r and r squared. You can hit second enter to bring that command back up, and you should get r and r squared at this point. So when they say, tell us to describe what we see in a scatter plot, I want you to think of this acronym, SOFA. Okay? So when you describe what you see in a scatter plot, when you talk about the association between two variables, you want to make sure that you address all 4 of these letters, and I'll show you what I mean. You want to talk about the strength of the relationship. Is it very strong? Is it weak? Is it moderate? Okay. Are there any outliers? Now, in this chapter, we don't have a 1.5 IQR test for outliers. In the case of the outlier, we just look to see if there's a point that doesn't fit the overall pattern. Like, so I look at this scatter plot here. If all of a sudden there was a point here, doesn't really fit the overall pattern, right? Here, generally, as this sprint time gets larger, the long jump distance is getting shorter. So this point here wouldn't fit that overall pattern. We'd consider that an outlier. What is the form? So generally, we're looking for only linear forms. And you don't want to get too carried away with this. We did this a little bit with our normal probability plot. But so if I saw a scatter plot that looked something like this, let's say. Okay, you can kind of see that there's a curving or a bending in that scatter plot. So a line, a linear model, probably might not be the best fit for that. So when we try to draw a straight line to it, we can see we're going to have a decent amount of error and a bunch of points on one side and then on the next side of it. When I look at this scatter plot up here, it seems like a line fits it reasonably well. Again, we're not talking about the error, the residuals. We're always going to have these residuals, right? We're going to have prediction errors. Not every point is going to fall on the line. That's okay. But I don't see a curving or bending pattern in the scatter plot. So I would say that the form is generally linear, okay, unless I see that it's bending. And you'll have another tool in the next section to assess linearity. And then the association. Is the association positive or negative? That's it. Is it positive? Is it negative? So do we have a strong relationship? Is it linear or nonlinear? And is it positive or negative? And then also make sure that you address any outliers if there are any. So for me to describe what I'm seeing in this scatter plot here, between describe the scatter plot in previous example, the relationship between sprint time and long jump distances. Okay, so it appears that there's so something along the lines of here. Notice I'm addressing strength. I said that it's strong. If you said it was moderate, I wouldn't disagree with that. If you said it was weak, I probably would disagree with that. It looks pretty obvious that it's a negative association. So it's strong, it's negative, and I should say roughly linear. Okay, it appears there's a strong negative, let's say linear association, or roughly linear, linear association between sprint time and long jump. For larger sprint times, long jumps tend to be shorter. Okay, interpret R in context. So R tells us two things. It tells us strength and association. So R equals negative 0.4 means there is a strong, basically what I just said previously, there is a strong negative association between sprint and long jump. Now, notice I didn't say anything about linearity here because R does not tell me whether the association is linear or not. In order to figure out if the association is linear or not, you have to look at the scatter plot. We just look at the plot and we can observe whether there's a linear or nonlinear pattern in it. Now, the second question here says, what effect does the highlighted point in red have? Well, let's think about it. If we were able to take this point out, if it wasn't there anymore, which I can't do, it won't let me, but if I could somehow cover that up, okay, so ignore it, what would happen to the strength of the correlation? Well, let's think about it. Here, if I were to just kind of eyeball the line of best fit, right, probably does something like that. It's definitely negative. Well, a point up here is going to pull the line, it's going to pull that part of the line towards it, right? Since the line is a negative slope, it wants to be down towards the end here. Well, this point is going to pull the line up towards it, kind of reversing the grain of what the slope of the line truly is. So if we remove that point, the correlation would not be as strong. The correlation would still be negative, okay, but it would be a negative value with an absolute value closer to zero. Not close to zero, but maybe it drops into negative 0.7 territory, okay, rather than negative 0.84. I hear you. Okay, so here again, make a scatter plot to display the relationship. I'm not going to redo that. You have the steps previously here on how to make the scatter plot on your calculator. Scatter plot's already made for us. If we think about what the line of best fit would look like here, right, or least squares line, it might look something like that. Or you might look at this and say, this looks like it could be roughly linear, or, you might see sort of a curving bending pattern to the data here. All right, so depending on what you see when you look at that, and we'll be able to interpret it a little bit more intelligently as we move through the chapter. But you want to go through our acronym of SOFA, right? What is the strength of the association here, right? There appears to be a strong, right? Definitely positive, and then you're going to have to decide whether I generally would probably say it's a roughly linear association, but it is interesting that we have 3 points in a row here all on the same side of that least squares line. Not a lot of times that's not a good indication. That's kind of a lot of times an indication that there is a curving pattern there. So we want to say that there's a strong positive, and I wouldn't argue with you whether you said it was roughly linear or if you believed it was non-linear, okay? But you want to make sure that you comment on that, okay? So we have a strong positive, roughly linear association between the amount of sodium and the amount of fat, right? In other words, as the amount of sodium increases, it seems that the amount of fat in those sandwiches is also higher, okay? Strength, outliers form association. I don't see any outliers here, so I would not comment on the outliers. Okay, so it would look something like that. Strong, positive, roughly linear association between sodium and fat. Okay, here we have a different kind of line. This is not the line of best fit. This is the line of y equals x. And we have Peter and Elaine. They're both English teachers at a high school. Students think that Elaine is the harder grader, right? So Elaine and Peter decided to grade the same 10 essays and see how their scores compare. The correlation was r equals 0.98. So their scores definitely seem to be closely related. They have a positive correlation. If Peter gives a higher score, Elaine generally gives that essay a higher score as well, and vice versa. But here we have the line y equals x, and the line y equals x here is going to represent essays that they both scored the same, and it looks like there's probably only one. This one here, it looks like they both scored it to be around an 85. So if a point lies on that line y equals x, it means that Peter and Elaine graded it the same. So what we're finding here is that as we move along here, it looks like, so we'll take this point for example. Peter gave this point above a 50. Elaine gave it less than a 50, right? Peter gave this point, this one's close to the same score, but again, Elaine scored it lower. Peter scored it, looks like about a 60, and since it's below the line y equals x, the y coordinate is below 60. Okay, we have these 2 points here, right? Both 70-something, high 70, mid to high 70s, but again, mid to high 70s for Elaine would be up above the line. So it gives us some evidence that what the students are saying is probably true. Elaine seems to be the harder of the two graders, or she grades differently or has different criteria. They don't seem to always grade the same, and in general, Peter's scores tend to always be lower than what Elaine is scoring.